So the last thing to talk about, if we're interested in calculating work, is to remind ourselves of what's called the geometric interpretation of the integral. Remember, work is equal to the definite integral from a to b of f dot dr. So we have an integral. There is a geometrical interpretation of the integral, which you may or may not have seen. Let's pick out a simple expression. Sorry, we need some axes here. So this is the force versus position of some force we're going to pick out. Let's pick out a force that looks like this. That is one with a constant slope. Now we have seen a force with a constant slope. We saw the spring force, which would have the spring force was negative kx, right? This is a positive slope, so I'm not suggesting that this is a spring force, but the idea is we've seen something that has a constant slope. Not all forces do, but we'll say that this one does. So let's say that a particle undergoes a displacement from point A to B under the impetus of some force with a constant slope. This is, of course, related to position. It's not a constant force. But let's say that it goes from A to B, and here's the graph of that motion. Now, what this integral invites us to do is to look at the area underneath the curve, right, which I'm hatching here. So in this case, it looks like if I have some sort of value, this is f at b, right? So if it looks like, if I know this value, and I know the values along the x-axis here, I can calculate the work very easily by just looking at the area underneath that curve. That is what an integral represents. It's the area underneath the graph of this quantity versus this quantity. So in this case, I could just skip the integral altogether and go to my knowledge of geometry. And all right, so this thing has a height of fb, right? This value here. It's got a base of this, if a is 0, right? It's got a base of b, and I can say that therefore the work done here is equal to 1/2 my base times my height, and I get that out of it. Now, of course, not all situations are going to be this easy. If you have a graph that looks like this, right, where this is force versus displacement, well, that clearly is not just, it doesn't lend itself to a simple geometrical interpretation. We can still talk about the area underneath the curve. But we also, calculating this is probably non-trivial, so it's, in this case it would be easier to just actually evaluate the integral. I do want to talk about this though conceptually, because if you'll notice, I've got two quote-unquote areas under the curve. I've got this area above the curve, or I should say above the x-axis, and I've got an area below the x-axis. What does that represent? Well, in mathematics, we would say that the concept of a negative area doesn't make a whole lot of sense. But in physics here, what this can represent is negative work, right? Negative work is a thing. That's totally fine. If these two vectors are pointed in different directions, then the work done is negative. Think of a friction force. A friction force is always opposed to the direction of the motion. And so in the case of friction, this quantity always turns out to be negative. For other forces, it just depends, right? For gravity, this would be negative if the displacement was up, because gravity's pointed down. But if your displacement is down, gravity's down, then that would turn out to be positive work. So you've got to take into account the relative positions of these vectors. But negative work is a thing. So it looks like in this case, the black areas represent, or the black hatched areas represent positive work, and this, the orange hatched area would represent negative work. So if I want to know the total work done, it would be a situation of finding the area, the positive area, and then subtracting off the orange. You can call it the negative area if you want to. Let's do a simple example of that with an easier to characterize force. All right, so here's my force, here's my displacement, we'll say Fx, x here. Let's say that I have a force that starts off like this, but then somehow changes like this, and then comes back like this. Well, if I look for the area under the curve, you might notice that I've got some discontinuities in the first derivative here. So if I were doing this by direct integration, I would have to do it piecewise. There's nothing wrong with that. But in this case, I can probably just say, all right, this is doing some sort of positive work here. In other words, underneath the curve here, I've got some sort of area 1. And underneath this curve, underneath, right, it's above it, I've got some sort of area 2, but I can see that that's doing negative work. So if I'm looking for the total work done, it looks like I'm going to take area 1 minus area 2. As I've drawn it, it looks like it's 0. I didn't mean for that to happen, but it certainly looks like that's the case. But in general, you just figure out your positive areas and subtract from it your negative areas. And you get the total work done. It could be positive, it could be negative. It doesn't really matter. We're going to find out in a few sections how that affects the motion of the object. But for now, just take it that your work could be negative, and your areas, we can consider this to, you can either consider it a negative area or just consider it an area, and you know to subtract it because it's below the x-axis.